Hello everybody to the session Scaling SQL Server Beyond One Core. My name is Thomas Grohser and I'm with SQL Server for a very long time. When you look at what I've did over the time, I've worked a lot with Microsoft and I'm with SQL Server since the very beginning. I'm really looking forward to what SQL has to bring in the future, and I've tested a lot of configuration over the years, and this session today will share my knowledge that I gained about all the things CPU related and what you have to take care of when SQL Server needs to run on bigger and bigger machines, which are more and more commonly available. So, before we start with the whole session, the most important thing you have to learn when it comes to dealing with all these pieces of hardware and software, and even in the cloud these days, you have to learn how to compare apples and oranges. Yeah? Because no two manufacturers will provide you with the exact same information or type of information, so you can easily compare it. Yeah, one will you give you kilometers per hour, the other one will give you miles per hour, and all this, and you have to figure out how to compare them. The hard part is that sometimes the things get really mixed up and intertwined, and it's not that easy to look at this. Or even sometimes one option is disguised into the other option, so it's really hard to compare. And the hardest part in the whole game, even if you have a clear apple and a clear orange next to each other, there is this little thing called marketing that might disguise both of them as something very different. Yeah? So what I've learned a lot, that I had to sit back and figure out how to really compare these things. When we're talking today in this talk, I will always give recommendation for everything that I'll show you. I will give you a recommendation for which one of my 4 sample workloads that I normally use to test and compare, these are good or bad. So the first workload is low latency. Yeah, you have a very few number of connections, maybe just one, but you need the fastest possible response time. Yeah, this is low latency workload. Yeah, as you want to ask SQL a question and you want the answer as quickly as possible. The second one is high concurrency, or OLTP. That means you have lots of concurrent connection that ask SQL Server for simple, small parts of information, and you want them all to work and play nicely with each other and have them. The third one is high throughput. This is all kinds of data warehouse, analytics, decision support systems. You have a few, but very large, complex requests against the systems. And the fourth one is a generic server, which basically means it has to do all of the above and is most likely virtualized these days, or on a virtual machine. Yeah? So every time I talk about a topic, at the end, I will tell you if whatever I talked in that section is going to be a good thing for which one of these 4, and for which ones you should avoid them. Okay, before we start with the whole details about SQL Server, let's talk about scaling parallel workloads in theory. And before everything is, yeah, you might want to skip this because it's a real brain teaser, but I like to understand and tell people what this is all about and why it's not so easy before I go into the practical examples. We have 4 tools in our toolbox when it comes to scaling workload. One is optimize, number 2 is reduce, number 3 is scale up, and number 4 is scale out. Right? And each one of them has pros, cons, and everything. Optimize is you take what you have, all the steps, everything you're doing right now, and you try to get it more efficient. Add on an index, put in some query hint, rewrite the query, try to make it faster. Thing is, reduce is just figure out if all the work you're doing is actually necessary. You would be surprised how many times I find that certain tasks, especially in like processes that load data warehouses or something, are running every day, and then you figure out we don't need it at all. Scale up is you buy a bigger box. Yeah, you buy a bigger, faster machine and see if SQL Server by itself can figure it out. And scale out is the hardest one to do, is you figure out how you can spread the workload over many servers in parallel. There's lots of product that claims that they can do this automagically, but there is no magic. Yeah, unless you really, really help the systems, scaling out doesn't really perform well. So let's look at optimize. Yeah. We have a basic workload, W1, 2, 3, 4, that we have to do one after the other. And when we can optimize each one of these steps, they can run in a faster way, as we see in the second line. Yeah? And then the overall workload is done in a quicker way. I mean, that's very simple. I'm just trying to start with a simple one so you understand the more complex diagrams that come in a moment. Reduce is, yeah, we figure out that if we don't have to do step W2, we're going to be done faster. Yeah? And maybe we don't need step W4 as well, and so on. So reduce means we are removing step and work from the process. That's also very simple and easy to understand. Scale up means instead of doing the jobs W1 to WN sequentially one after the other, we put in more CPUs, more resources, we schedule them in parallel, and we run them all and hope at the end when we synchronize the results that everything is fine. So doing them in parallel will take a little bit longer than doing each one of them, or the longest one of them, but overall it seems to be much faster. The problem is that in reality, tasks have dependencies on each other. So we will not be able to run them all in parallel in a perfect way. So each one here is a simple example where each one kind of halfway depends on the other one to finish first before I can start the next one. You still get an overall gain in the performance, but it's not as ideal as if I can run everything in parallel. Yes. Scale out is basically the same as scale up, with one additional step at the beginning, at the end. We have to send out the tasks to the various machines. So we have to spread the workload across the machines, and then they have to send back the results to one coordinating machines. This one has to collect all the results, synchronize them, and then most likely have one more step to combine. So scale out only works when you have very, very large workloads. Because if you have small ones, it takes much longer to spread it out and slice it up and then combine it in the end than actually running the small portions on each and every machine. But if you have tasks where, like, you have hour-long processes and you can run 100 of them in parallel, so instead of 100 hours, you get only like 1.5 hours to process the whole thing. Scale out, if the tasks depend on each other, it gets really bad, because then all the machines constantly have to talk to each other and the scale gets really bad. Some very clever guy put all this into a very kind of simple formula, which is here, and it's hard to understand. P is basically how much can you run stuff in parallel. Yeah? How dependent is the stuff? Yeah? And that is entered in percentage. And S is how much is the speed up in this case. So when you plot this out into a nice little curve, where we have on the x-axis the number of processors on a logarithmic scale from 1 to 4,096 CPU cores. And on the y-axis, we have how many times faster something will run. And the various curves in various colors show, as the legend shows, how much in parallel, how little they depend on each other. So if they depend 20% on each other, you basically see no improvement over like 16 cores. After 16 cores, you will not see this thing go any faster. If you only have like 2 or 3%, you can see a speed up to 50 times when you go bigger. But again, you normally see the curve flattening out at around 256 cores. If you go to 99%, which is really, really independent workloads, then you are already up at, you scale nicely all the way up to probably 512 cores, and then the flattening out happens. Let's translate that into SQL Server. If we apply this Amdahl's law to SQL Server and machines that you can basically have today, is SQL can run queries independent from each other at about 97 to 99%. It really depends what kind of workload you have and how they run and how much you have mixed insert updates and queries at the same time, or if you're just a data warehouse where you load once a day and then just read. It varies, but somewhere between 97 and 99%. And if you plot that over how many cores it is, you see that it basically stops somewhere between 128 and 256 cores to become efficient to add more cores. You can still see in the best case scenarios that you will gain a little bit more, but overall, really it doesn't matter if you have 128 or 256. If you can't separate your workload, you can't. Just to be very clear, this is when one query tries to scale out in parallel. If you have two queries that run on completely independent data sets, they can scale completely independent from each other. But keep in mind, SQL Server has metadata, and that metadata is always shared. And this is where this 1% comes in, that you will always have some like 1% dependency on queries on each other. SQL is really good in scaling up, actually, or scaling out. Good. So let's look at practical scenarios. A long time ago, in a server far, far away, we had one core, one CPU, some memory, and some I/O. This was really, we're talking 1980s. This is the design in the 1980s. And it was simple and easy to understand. The CPU accessed memory, talked to the I/O devices, and moved data around. And there was nothing much when you were writing code. You were writing code in a very sequential way. Everything was done one step at a time, and nobody had to be careful about anything. Yeah? But over time, this quickly changed because things got faster and faster, and not all the components could grow at the same time. So the first thing that was added to CPU cores was cache, because memory is really slow compared to the CPU itself. So putting some really, really fast and expensive memory inside the CPU that operates as a cache makes it much faster. And since I said it's very, very expensive, they came up with up to 3 levels where each level is a little bit slower than the previous one, but also much cheaper, and therefore you can have more and more of it. So in today's CPUs, level 3 cache goes into the hundreds of megabytes, but level 2 and level 1 are still like in the level 1 is still in the kilobyte range, and level 2 is somewhere in the 1, maybe 2 megabyte ranges. Yeah. The difference now is if the CPU core wants to access memory, it will just look in the cache first. If it's not in the cache, then the cache will ask the next higher level cache, do you have it? And so on. And if the L3 cache doesn't have it, it will actually pull it from memory into cache and then make it available to the CPU. The chances are with most programs that when you when you access some memory, you will access it in the near future again. And this is where the cache makes it really fast. Also, what happens is that cache is not just pulled in the exact amount of data you ask for. They pull in a whole cache line, which is usually 64 bytes. So, for example, if a program goes through an array and they pull in 64 bytes, it can, for example, already have then the next 63 characters when it goes through that string or something is already in cache, and it can access it much faster. Good. Then, after adding caches, they started adding multiple cores to CPUs. And when you have multiple cores, it makes sense to also give each core its independent L1 and L2 cache. L3 caches are usually shared between multiple cores, if not all the cores. Thing is, what makes things now complicated is that the L1 and L2 cache from each one of the cores have to talk to each other because it will what if core 0 just accessed a certain location in memory, which is now in its cache, and then core 1 wants to access it, and if it would pull it out of memory, it could get a different value. So the caches now also have to talk to each other before talking to the next level, so that when multiple cores need to access the same memory value, they make sure that you get the most current value. But that also shows that now programmers, like the people that write SQL Server, have to take care of it. And it also shows that there might be a potential if we can arrange where data lives and which core accesses which data, we might, as we learn later in this presentation, that we can optimize and help SQL Server have the data in the right cache. Modern CPUs are built in various different ways. So let's look at the most traditional one. You have a single chip inside the CPU, a single die, they're called dies, that has, in this example, 8 cores. It has 48 PCI Express lanes to talk to I/O, and it has 12 supports 12 slots of memory. And this is a typical Intel CPU with 8 cores. They have a relatively high clock speed, and it also has 3 QPI connections where it could talk to other CPUs to exchange information with them. If the CPU would have more cores, it would look like exactly the same way. It would have the same PCI, it would have the same memory, but it has more cores in it. What this is usually the result for, the more cores a CPU has, the lower the clock speed is. So this is something where you can have to choose, do I want a high frequency or do I want a high core count? Yes. So use cases for single CPU. As I said, our 4 sample workloads, low latency machines can only run on a single CPU. If you want the lowest possible latency, you cannot have a second CPU. And the second one, generic servers, also work very well these days on single CPUs. The main reason is there's now single CPUs with 64 cores plus hyperthreading. That's 128 threads you can run on. That's a lot of computing power. Most SQL servers are very, very happy with that, and already very expensive through licensing. Right? Also, for low latency, you want the highest possible clock speed and not too many cores, because you only have very few connections anyway, so it's better to have a few connections run on an highest possible clock speed. For generic servers, you want probably more cores, but still not multiple CPUs. The next one I've mentioned already is something called hyperthreading. Hyperthreading is something that was introduced many, many years ago, and it basically allows you to have each core can have a second virtual core assigned to it. So when you have no hyperthreading or hyperthreading turned off, you have all your thread states in your CPU, like your registers, your flags, and the program counter, and the stack counter, and the stack pointer, and all this stuff once. And you have all the arithmetic, floating point, multimedia extensions, all of them, you have them a single time. And whenever your program runs and needs to use either one of these math or floating point stuff, it immediately can use them and is a happy camper. If you have hyperthreading on, you have the thread states twice. You have thread A and thread B on the same core. Yeah, they have completely independent registers, completely independent flags, and they have completely independent program counters and all that stuff. So what now happens is if thread A needs the arithmetic unit, it will access it and use it. If thread B at the same time runs a different thread and needs the floating point unit, it can use it independently, which is great. Problem comes if both thread A and B want to use the floating point unit at the same time, then we have the problem that one has to wait till the other is done. Um, Hyperthreading is one of these many things. It's neither good nor bad. It depends what you expect from the system. Yeah? From a single thread perspective, you lose about 30 to 40% of performance because you have occasionally wait for the other guy to free the resources you want to use. But if you look at an overall performance over all the threads running at the same time, you're gaining between 20 and 40%. Yeah? And this depends on which type of program and so on. Usually with SQL Server, it's about 30-30. So you lose 30% on the single thread, and you gain 30% in the overall when you turn it on. So when to use hyperthreading? Low latency, definitely not. High concurrency or OLTP, when you have lots of things running at the same time, I would not use it unless you have so many concurrent threads that you would run out of threads to operate on. Then you might want to turn it on. Where it's really good and where it helps your overall performance is in any kind of data warehouse. Yeah? And usually in generic servers, overall, you will gain some overall performance through hyperthreading. But be aware that an individual query might now take longer, but you can run 30% more queries in the same time. So again, it's a trade-off, and you will have to make these decisions. Adding a second CPU. So far, we only talked about one CPU and what goes on within one CPU. When you have a second CPU, it gets a little bit more complicated. In theory, you have now these two CPUs with two cores each, and now we have to connect them. But now also the caches have not just to check with the caches in the same CPU, they have to also talk to the other CPU and ensure that these caches don't have data they need or they want to access have it too. And this now also expands to the level 3 cache that before was shared between all the cores. Now it's independent L3 caches between the two CPUs. Yeah, so basically, and you have the memory connected to each one of the CPUs. So the caches on each side also need a way to talk to the memory of the other CPU, which is normally done through these QPI links, or AMD just calls it, uses PCI Express lanes for it, but it's the same kind of operation. One CPU has to ask the other CPU if it's not in its own memory space to hand over the data from the memory the other CPU manages. Right? As you can imagine, this complicates things already. And to give you some practical example, memory access. So the time it takes to get memory on a single CPU, and memory access is 76 nanoseconds if you have just one CPU. If you add a second CPU and do the exact same memory access on the same that is local to your CPU, you have about 98 nanoseconds. So you're adding about 13 nanoseconds to the whole process just because you have to check with the other CPU if they have anything that you are looking for in any of their caches. And I mean, it's not a long time, but each and every memory access is now a little bit slower. Yeah? If you need the same memory from the others, that if you need a memory access from the other CPU, it becomes 139 nanoseconds. So you have to ask the other guy to give it to you. He will do everything he needs. He already knows that it doesn't have to verify with you back, but loads it into its own and then hands it over to you. That just takes an additional about 40 nanoseconds or 50 nanoseconds. So you can see that adding a second CPU complicates things. Lucky for us, we don't have to deal with the nitty-gritty details, but it will Uh, we have to, if we have two CPUs in a server, we should start helping SQL Server to put its data into the right memory. So it's on the CPU, it will actually need it. There's also the option, there's some CPUs on the market that are actually two independent CPUs. Um, yes, so if you have two CPUs, as I said before, you connect them through these QPI lanes where they talk to each other and exchange and check if it's in the cache of the other guy, and if it's from the memory of the other guy, they transport it between them. Yeah. And there is some CPUs out there that claim to have more cores, but in reality, they are actually two independent CPUs that are in one box, and then they use the QPI links internally to link the two independent CPUs. So you're not getting a 56 core CPU, you're getting actually two 28s, as if you have two independent CPUs in your server. So careful there. When you buy CPUs, check if they are actually one or two CPUs internally before making the decision, because that could change the outcome. Um, Intel's competition, AMD, goes with a different design. They use multi-dies to begin with, so they always put eight cores on one die, put level 3 cache for that, and then have in the middle a big thing, an IO manager, memory manager in the middle that coordinates all that. This works surprisingly well, and SQL does very well with that. They also right now have way more cache than the Intel competition. They have more cores available. They run partially in higher clock speeds. So overall, at the moment, I'm seeing better results with AMD CPUs. Yeah. And they're coming out soon with models that have an insane amount of cache. We're talking like 3/4 of a gigabyte cache in the L3 cache, and that allows them to keep parts of your data in cache, not just few instructions and the current page or something. No, no, we're talking parts of tables that are in cache. If you have two CPUs and two dies each, that's the ones we talked before, and you connect them, you are actually having a four CPU machine, and four CPU machines right now have no practical use. This is something you have to be very careful. Intel can go up to 56 cores with two CPUs and 112 with four. The problem when you take an AMD CPU, a single one can do 64, two of them can do 128, which is already more than 112 that four Intel can do. Yeah? And two CPUs work always better than four, because once you go to this four CPU design, as you can see, instead of each CPU talking to the other one with three QPI lanes, now each one talks to each one of the others through one. So if two CPUs have to exchange data now, that's happening at 1/3 of the speed than it happened before. And of course, you can have more memory and stuff like this, but still, the more CPUs you have, the more headache you have with scaling. So let's look at which machines benefit from dual CPUs. Generic and virtualization servers. With all the other ones, I would not use dual CPU machines right now. That's current recommendation. Four CPUs. As you can see, four CPUs or two dual die CPUs are the exact same picture. It's just the borders around the CPUs are drawn very slightly. And when you go through this recording later, you can just skip back and look at this. As I said before, right now there's no practical use case for four CPUs. Just unless you need super extra I/O that four CPUs can give you, or you have an edge case where you need the exact amount of memory that four CPUs can give you and two can't, then yes. But in general, a four socket machine right now doesn't make any sense. Eight CPUs, they make sense because they can grow bigger than two CPUs on AMD. They are only available with Intel. AMD does not provide any models right now that go beyond two, but Intel can stack them up to eight. What you can see in this diagram is that when you have eight CPUs, not all CPUs are connected to each other anymore. They are connected by this twisted cube um, that is drawn here flattened out. So some CPUs are connected directly, other CPUs need um, one hop through another CPU. But everybody can talk either directly or with one hop to another CPU. So, for example, CPU 6 when you go from there and you want to go to CPU 0, you have to hop to number 2 and then get to 0. I guess. Yeah. If 6 wants to talk to 5, it can do it directly, 7 directly. If it wants to go 4, it has to go through 7 or through 5. If it wants to go through 3, it has to go through 7. If it wants to go to 1, it has to go through 5. And we already talked about 0 and 2. Yeah? So it can reach everybody. It just has to choose sometimes a helper in the middle. And you can imagine that this slows down things again. So we now have three memory access latencies, the two that we had before, local and the neighboring CPU, plus now we have the third one when it has to go through another CPU. Yeah. And the bandwidth between CPUs is down to one third of the dual socket. That's the same as in all. It's even a little bit less because if, unfortunately, CPU 6 and 5 want to talk to each other at the same time as 1 and 6, then the connection between 5 and 6 gets really clogged. Yeah. Good. So, I will skip 16 because 16 is just 32 cut in half. But with 32 CPUs, it's a design that looks like this. Yes, they are possible. SQL Server runs just fine on machines like this. There's right now, to my knowledge, one company that makes them. They're called Superdome X. Um, and what they basically do is they take four socket machines and instead of cross connect the CPUs, they connect each and every CPU with the third QPI to an ASIC and then have each and every ASIC talk to each and every other ASIC. The ASIC is just some logic they built that basically takes the requests from the CPUs and talks to the other. The nice thing about this is it's not much worse than an 8 CPU. So, and with worse, I mean compared to a single or dual socket machine. Yeah? When you go from 8 to 32, it's not like when you go to from 2 to 8, you cut down to one third or one sixth of the bandwidth between the cores and you add extra latency. When you go from 8 to 32, it doesn't get much worse. It just basically stays where it is. And that's the nice and the beauty of this design. That when you go from 8 to 32, you're not making it any more slower. Yeah? You're just making it more complex, but that complexity helps you do. Yeah? Within a 4 CPU node, it's the same as an 8 socket. Yeah? And through these ASICs, the communication makes it really, really nice thing. So you almost have the same speed as in an 8 CPU. And usually in a machine that big, you will start helping SQL Server to do the work much better. Good. So when to use 4, 8, and more CPU systems. High concurrency OLTP. This is because you need as many cores as possible. Thing is, yeah? Don't get me wrong. There's probably many two socket machines these days that can also handle high concurrency. But I'm talking you need 10,000 people talking to the machine at the same time. You might want to have more than two CPUs. And of course, if you build gigantic data warehouses, you want these more CPU machines, if not just for the more I/O they provide, and therefore allow you to connect to your storage much, much faster. Yeah. Generic machines makes no sense. Low latency makes no sense at all. Okay. Moving on. to NUMA. NUMA is an acronym standing for Non-Uniform Memory Access. And we kind of talked about it already. It's just a technical term. If you have more than one CPU and you need to access the memory that is connected to the other CPU, it takes longer than accessing the memory that is connected to yourself. And that's exactly what NUMA is. Um, the difference is that NUMA, from the perspective of software, is a good thing, while non-uniform memory access from the hardware side is actually, when you have it, it's bad, because the thing is, and some hardware machines actually let you turn it off. The problem is that's not a good thing on the hardware level, because on the hardware level, instead of making the remote access faster, what they're doing is they're putting an extra pause on the local system, and therefore now have the memory access being the same regardless if it's remote or local. Some really old software that had no idea how to deal with the faster access and was doing timing through memory access or something had problems, and this switch is only there. Never turn off NUMA on the hardware level. NUMA is your friend. NUMA is not your enemy. Yeah? You just have to learn how to talk to your friend and how to talk with it. And this is what we're going to discuss right now. So in a normal system, you have a network card where your request comes in, you have a CPU and you have memory, and that memory holds all the data that it will need. Yeah? We're ignoring I/O and storage right now because it's not relevant much here. So if you have that and then you add another CPU, you still have the one network card, and your data is now 50-50 between the CPUs, and you're either half the time you're going to be lucky, half the time you're going to be unlucky. The problem is if you add more and more CPUs, you getting more and more unlucky, because in this case you will be 3 times unlucky and only 1 time lucky that the data is on the CPU you're connecting through with the network card. And this gets even worse. So what you do is, to fully embrace NUMA, you would have one network card per CPU. So if you have one CPU, you have one network card. If you have 2 CPUs, you have 2. If you have 4, you have 4, 8, 8, and so on. Yes, on a 32 socket system, I would recommend having 32 network cards, or at least one network card for each one of these 4 CPU nodes that we looked at. What you can do then now is to have your clients know which one network cards to connect to get to certain data. You could, for example, say all customer data is on the first network card. All queries regarding to inventory go to the second card. All queries regarding sales history go to the third one, and so on. Yeah, that's probably not a much scaly process. But what you could do is, if you say, okay, I'll take my customer ID and divide it equally all my customers between the 8 cards by using like a function like modulo or some other hash function to figure out which one of the 8 cards to use in this example, whichever one you have. In a for example 2-socket system, you would have 2 network cards, so it would be very simple. All even custom IDs go to one CPU, go to the first one. All ones go to the second one, or the other way around. Doesn't matter. What you do then, and SQL Server is really good at that. SQL Server will always try to allocate local memory first. Yeah. And then what you will end up with is that each one of these CPUs had a certain range of your data, and then could immediately, directly, when you have a request against the third one, for example, it would immediately go to the same CPU that's connected to the network card, and this one would have it in its local memory. And if at the same time someone goes to network card number 6, that one would happen again, and they could, completely independent from each other, serve the request and be happy. Remember, metadata will always be across all them, so there is some crosstalk, but it's much, much less. Yeah? With this behavior, I could gain up to 15% more performance by just putting in a bunch of cheap network cards and adding a couple of lines of codes in the client to figure out which one to connect. 15% on a large machine is a lot. Yeah. Remember, these larger machines might have 100, 200, 300, 500 cores. If you get 15% out of it, that's a lot of licenses saved because you don't need a bigger one. Soft NUMA is a second layer that SQL Server supports to even more granular break it up. With hardware NUMA, you can align network cards, CPUs, and memory. With soft NUMA, you can align the cores inside the CPU with certain ranges of memory connected to that CPU. So before, we divided this whole thing by 8 into 8 different piles, and now we're even subdividing it by into for each and every core. So if you have CPUs with say 16 cores, you could define 16 different ports and assign each one of them to a specific core, and then have the data even partitioned more and assigned directly to that. Which will that give you? That will give you that the likelihood of having the data in the cache is even higher than it was before of that specific core. That is great, and it makes it faster, but only by about 5 to 6%. So why would I still do it? Because it costs nothing. There's no extra hardware. There's no extra thing. It's again a couple of more lines configuring SQL Server and a couple of more lines in the client application. Right? And again, this talk was about how to scale as much as you can and as efficiently as you can. So this is it. The next topic we're talking here about are called super and sub ledgers. Yeah. SQL Server, when accessing memory, it protects the memory by something called a ledge. It's basically the moment any core needs to read a data page of SQL Server, it flips a bit and says, this one is used. And now everybody else that tries to access it sees it's used right now. I can't go there. I have to wait. Yeah. And these are you might see them occasionally in your queries, which are called page ledge something. Yeah. There are certain pages inside of SQL Server that I used a lot, and this is where super ledges come in. And the nice thing about super ledges, you don't have to do anything. SQL Server just does them for you. Yeah. So what happens is, if you have a lot of CPUs or a lot of cores, and SQL Server notices that there is real big contention on some pages, and these pages are mostly read-only. Yeah. For example, the root page of an index. Yeah. Every time someone has to do an index lookup, they have to go to the root page of the index. But the index root page rarely changes because there has to be a lot of changes underneath it for it to actually have to change. So what happens is they make a copy of that index root page in every NUMA or soft NUMA partition of the memory, so that it's always readable locally. Yeah? And if a write change to this memory page has to occur, then SQL Server has to obtain a ledge on each and every copy, make the changes in all places, and then put it back to normal. Yeah? This is a wonderful feature. It's built in, and the moment your machine goes big, this will turn on automatically and make things go smoother. Yeah, it's just one of the many magic features in SQL Server. You probably didn't know that it worked. You probably would sleep well, but it's taking care of you. So you don't have to have a crazy idea of like duplicating an index 3 times so that 3 different threads could work on it at the same time. No, SQL does that for you when it's necessary. Yeah. So already said for writes, it has to grab them all. So when would I actively support NUMA? Yeah. When would I put in the work? Yeah. Definitely on low latency machines. Yeah. I would, thing is, since on a low latency machine, there should be no NUMA nodes, that should be fairly easy. But even the soft NUMA nodes, if I have multiple cores, I might still find a way to make it a little bit faster there if I affinitize. If I have, for example, two different processes using the same machine, I would assign one to this soft NUMA node, the other one to the other, so they work in their area as best as possible. Yeah. Again, low latency, you want the fastest possible, you have to put in the work. Yeah. High concurrency OLTP, that's definitely the place where this was made for. Yeah. You need to have thousands and thousands of customers. If you have them and you can pre-sort them so that a group of them is in a bucket at a time, that's much easier. Just compare this to when you have a big um, government building where you like get your passports. They usually, when you go in, they sort you by name. Yeah. A, B, C, D, E, go in this lane, and so on. Yeah, because it's much easier for them to look everything up and they don't have to run around between all the things. Yeah. And this is exactly the same concept, just translated into SQL Server. The other two, high throughput and generic servers, it's not usually worth the effort. Yeah? Don't do anything to turn it off. Let SQL Server do whatever it wants to do by itself, but you don't actively support them. In the two first workloads, if this is what you do, it makes a lot of sense. CPU affinity. So, one of the last topics we're going to touch. CPU affinity is, let's say we have a simple machine with two cores. SQL Server would create a scheduler on each one of these cores. And then you have a query coming in, and the query gets assigned to a worker thread, and then the worker thread gets assigned to a scheduler randomly. Not randomly, a scheduler that is not busy right now. If you have a lot of stuff running, then the worker might have to wait for a while, but it usually finds something very quickly. So if this runs now, and after a while, the SQL Server OS tells you, "Hey, you've used the CPU long enough. Go away, make space for someone else," and then it will be scheduled again. It might end up on a different scheduler. And this might pop back and forth. And changing schedulers means that whatever was in the cache on that core before is for sure not in the cache on the other one. Yeah. And if these two schedulers are actually across CPU boundaries and not just within cores within a CPU, these reschedules can be very, very expensive. Yeah. But that's the default behavior so that nothing can get stuck. Yeah. I guess. This, and I'll zoom in immediately. This is the dialog where you can change that. If you click processor affinity on all, or you can be funny and tick each one, then you change that behavior so that once a query is assigned to a worker and that worker is assigned to a scheduler, it will not change the schedule until it's done. Yeah? This is, as always, good and bad at the same time, and it really depends on your workload if you should do that or not. Yeah? Just imagine that you have two schedulers and three queries. Yeah? So the first one gets assigned to the first scheduler, the second one to the second, and then the third one is assigned to one of the two. And even it might be that the first query is going to finish after 5 milliseconds, the second one is going to run for the next hour, and you get placed on the second core because at that point it looked like it was doing less. Yeah. And then now you are stuck with that other thread that runs for the next 2 hours while the first core is completely unbusy, but you will never be moving. So if you have very long running queries, I would not turn that on. Yeah. But if you have thousands of very small queries where moving them around is a bad idea, it makes total sense. To turn this on, you can either use the GUI as shown before, or you can use these T-SQL commands. Auto is basically turning it off. It doesn't do any affinitizing. Yeah, so it allows you to migrate between alls, and this is in the GUI if nothing is checked. Yeah, if you set the affinity by assigning certain schedulers, affinitize to certain schedulers, then you have the sticky operation. And you can also limit to just use a certain amount of cores. Yeah, this might be helpful if you run more than one instance on SQL Server or run some other software besides SQL Server on the same machine. They both can say, hey, I'll stick in this corner of the machine, you stick in that corner, and we're both happy. There you can set the affinity plus you turn on trace flag 8002. That gives you the behavior of auto, but only on the cores you selected. So if you want SQL to run only on half the cores, you can affinitize that and set that trace flag, and then SQL will only schedule between the cores, but with its normal behavior of moving around. This you would use if you have multiple instances of SQL Server and you have generic workloads. Yeah. So when would you set CPU affinity? Definitely in low latency. Low latency, it's a must because if you have to change between cores, your latency is bad. Yeah. So stick with it. And low latency also means we're going to be done quickly. So on low latency machines, CPU affinity is a must. High concurrency, the same thing. You have thousands of small queries. Yeah. Don't let SQL Server waste time with moving them around. You know that all the queries are fast, so you can tell SQL Server once you start, you stick with it. You still swap between the threads, but you don't unload and move them to another core. Yeah, not a good idea on any kind of data warehouse load where you have long running queries. They're complex. You don't know how long they run, and you have multiples of them. Very bad idea there. And the same, it's a bad idea on generic servers because you have no idea if you have long and short ones mixed up. Thing is, yeah, this works only if you have very short queries, but it makes them run faster. That's the summary. Okay, we yes. So. Uh, One of the very last things I'm going to talk about is also you have to balance system resources between the CPUs. Yeah. So if you have more than one CPU, you have to connect your memory, your disks, your network cards to both of them. Yeah. You cannot imagine how many times I see systems where each CPU has memory and then all the disks and all the network cards are connected to the first CPU and nothing is to the second CPU. Just imagine we talked a lot about memory access and all that. The same goes for disk access. Yeah. If each and every CPU has half the disks, there's a 50-50 chance it can directly talk to the disk and load the data. Same goes with network. Yeah. Network, even the NUMA thing, you need to connect them to each and every CPU. Yeah. The reason why most vendors ship them in the second way is because their machines are optionally with one or two CPUs. And if there's only one CPU in it, everything has to be on the first CPU. So just as a precaution, and that's the explanation, they put everything on the first CPU by default, unless you tell them otherwise or you do it yourself. And this is, I got the question recently in another version of that presentation. Someone asked, how do I connect this CPU, this network card to this CPU? This is a physical connection. So there's literally cables going from that CPU to the various PCI Express ports. And you have to look up which one of your expansion ports is connected to which CPU. That's usually in the manual, and then you put half on each CPU. Yeah, it's usually either all the cards on the left side of the machine are for one CPU, and all the ones on the other side are for the other, or other vendors interleave them like slot 0, 1, 0, 2, 4, 6 are for one CPU and 1, 3, 5, 7 are for the other one. Something like this. You have to figure it out for your machine. It's different everywhere, but it's super easy to make sure that everything is balanced. So don't use that. Use the first one. I've even seen vendors that do the really horrible thing where they put all the memory on one CPU and just put the second one to do calculations. That's really bad for database workloads. If you're just a number crunching software, that's actually like kind of acceptable. But for databases, that's really, really bad. Yeah. So high concurrency and throughput. So one last thing I want to talk about the same thing. If you have large machines like 8 socket, and they're connected like this, and you connect a bunch of disks. Don't go into the details. Maybe if you guys give me great feedback, which I will ask for in a few, I can come back next year, and this presentation is a part two called Scaling Beyond One Disk, where we talk about the disk thing in more detail. What I want to say, which is the most relevant part to the CPU, if you add a disk and you put RAID on it, software RAID on it, make sure that either both disks are connected to the same CPU or to CPUs that are directly connected to each other so they can easily talk to each other. If you connect a RAID 1 to like this, CPU 7 and 1, then every time you write to it, CPU 3 gets busy as well. And that's a real bad idea. Yeah? So don't do case number 3 here. Just connect directly. Yeah? I didn't remove the part on the right. Just ignore it for now. But just if you have a larger system, you have to take this under consideration when you do all uh, the parts. So, uh, thank you very much. tg@grohser.com is my email address. As I understand, we are at this time we're already chatting in the chat and answering back and forth questions. Or if you haven't started, now is a good idea. If you have any questions, you can ask it in the chat. If there's not enough time, or you come about something later, or you don't want the public to see your question, you can email me after the presentation. At this time, the slide should already be uploaded, and so you can have access to that email address later. We also have to thank Microsoft for sponsoring and supporting the data platform geeks and SQL Server geeks community, including this summit here. Thank you very much, Microsoft, for making lots of these things possible. Thank you as the audience as well. There's ways to win prizes, and please give feedback, what you liked, what you were missing. If you have any ideas or anything that I should add in the future, if I do this again, please let me know. It's the only way. Unfortunately, we are still not in a room together. We are still virtually, which is great because we are probably having a much bigger audience. But it's also sad because I really like to, after these things, talk to you in person, but that's not possible. I will be on the chat for the next, I think it's 15 minutes. Don't quote me on that if that's wrong. I will be there as long as they let me and as long as you have questions for me. And if not, if the software is anything like last year, we can find some place afterwards where we can chat in some of the community areas. Thank you very much for listening to me. It was a long talk for me, but I hope you learned something, and I hope one day to see you all in person again. Enjoy the rest of the summit, and as I said, I will answer questions as long as you have them.